Okay, so my name is Marc Newlin, and I'll be talking about a GNU Radio module and Wireshark dissector we're open sourcing today to interact with these Nordic Semiconductor nRF24L series of transceivers. So I work as a security researcher at Bastille, and I spend a lot of time using software-defined radios to interact with different types of proprietary and standardized wireless protocols. And I've taken kind of a non-standard route to get into the SDR space, so I just want to talk about that for a second and highlight the fact that you don't necessarily need the traditional academic background to do meaningful work in this space. So in 2011, I competed in the DARPA Shredder Challenge. And this was a competition to figure out how to reassemble shredded documents. And it was my first time doing anything on that competitive nature, but I ended up doing pretty well, and I finished that in 3rd place out of the 9,000 or so teams. And so I decided that I would sign up for any future DARPA challenges that were made feasible to do in my spare time. So in 2013, DARPA announced a Spectrum Challenge. And I hadn't heard of SDR at this point, but I decided to sign up anyway. I was still pretty confident from the Shredder Challenge. And there's this 3-week period between signing up for the challenge and the qualification round. And I used that 3 weeks to learn just enough GNU Radio to be dangerous, and I managed to qualify as a finalist and ended up doing pretty well in that. And I had the distinction of being the only finalist who hadn't gone to college and was also the only solo finalist team. And so the point is that if you have reasonable software skills, you can use GNU Radio to abstract away the math and signal processing and still do some pretty neat stuff. Then at Bastille, I've been behind the Mousejack and Keysniffer projects. And these are a series of keystroke sniffing and injection vulnerabilities I found in non-Bluetooth wireless mice and keyboards. And most of these wireless mice and keyboards use these transceivers from Nordic Semiconductor. And so you have 5 or so chips in this family. You have ones with and without embedded microcontroller, with and without AES and USB support, but they're all compatible over the air. And so most of these common wireless mice and keyboards, you're going to have one of these transceivers. And so they can be called a 2.4 gigahertz ISM transceiver, but really they operate just outside of that band as well. So you can tune them between 2400 and 25 megahertz. It's all GFSK modulation. They have some physical and MAC layer functionality built into these chips, but it's still customizable to an extent. So you can have 250K, 1 megabit, or 2 megabit data rates. You have 3 different address widths you can specify. You have variable length payload between 0 and 32 bytes. You have an optional 1 or 2 byte CRC, or mandatory 1 or 2 byte CRC depending on the specific protocol you're using. And there's no whitening or error correction built in. So it's a pretty simple, low-powered GFSK protocol, kind of like BLE, but with a few tweaks. So they have this protocol called Shockburst, and this is the legacy that's used by some of the older chips. So in this, you have a fixed length payload. You have a 3 to 5 byte address, and then you have this optional 1 or 2 byte CRC. You can also forego the CRC. But most of the modern devices use the enhanced Shockburst protocol. This adds this packet control field, which has a sequence number, a payload length, and then a bit you can set to request that no ACK is sent. With this, you have this variable length payload, and because you have the sequence number and the ability to do ACKs, the chip itself abstracts away automatic ACKing and automatic retransmit. So from the standpoint of using these, it's pretty convenient. You say, I want to send this payload to this address with this ACK timeout and this many retransmits. The way the addressing works is a little bit quirky. You can listen on up to 6 addresses per time per chip. 2 of the addresses can be unique on all 5 bytes, but the upper 4 addresses can only differ by the upper 1 byte. And the common use case is this star network topology, where you'll have a USB dongle plugged into a computer. You'll have the USB dongle listening on up to 6 paired devices in a typical case. And then each paired device then transmits to the address of that USB dongle. And so it's good for this case where you have this star network where you have one device communicating with 5 or 6 others. So commonly you'll have these USB dongles with wireless mice and keyboards. You'll have the chips in these devices. In the bottom right, you have what's commonly used with Arduino. So this is the nRF24L01. This is without an embedded microcontroller, and it's controlled over SPI. So if you've done any kind of Arduino wireless comms, you might have used one of these. In the upper left, this is a Crazy radio dongle. This is part of the CrazyFly open source quadcopter project. And this is one with an embedded microcontroller. And it also has an LNA and PA chip on there, so you can do fairly long-range comms. The bottom left, you have one without the 8051 and with the LNA and PA as well. So a lot of these are fairly common iterations of this type of chip. So commonly, you'll have these wireless mice and keyboards, trackpads, presentation clickers, the number of quadcopters which use these, and then a lot of DIY projects. So this GIF here, this is a hat I built for Burning Man last year. And I had a TNZ in the controller, TNZ in the hat, and I ended up using these NRF chips in the controller in the hat. And this is actually where this whole mousetrack and key sniffer project started, because I modified the controller to hijack mice at DEF CON last year. This is the inside of the controller, just for an example of how you might use these kind of things. I ended up cramming all kinds of radios in there. And so you have these chips, and what you want to do is be able to sniff traffic with it. And the problem is the actual address is also used for the sync word. So you have the preamble, then you have the address. With the chip, you tell it what address you want to listen to, but if you don't know the address of an unknown device, you can't sniff on it. So Travis Goodspeed figured out this pseudo promiscuous mode you can invoke back in 2011. And so the manual specifies a 3, 4, or 5 byte address, and it says for what would be address length 2, specifies as illegal. But it turns out you can actually set that to an address. And Travis figured out that you can set the address to 0055 or 00AA, which gives you 00 and then one of the two possible preambles. And by doing this, the chip will actually send to the microcontroller over SPI any bytes that follow that preamble. And this gives you kind of an approximation of sniffing, because you can see some of the packets that go over the air, but because you're just matching on this preamble, you're going to get a lot of false positives. So as part of this mousetrack and key sniffer project, I wrote some firmware that runs on the version of this chip with the embedded microcontroller. This takes advantage of Travis's promiscuous mode hack and makes it possible to do this generic sniffing and transmission with these USB dongles or with the Logitech USB dongles you can flash the firmware onto. And this works pretty well, but the problem is you can't see 100% of the packets, and so it's useful for kind of playing around, but you can't do very good sniffing with this. So the point of GR Nordic is to address this problem and use software-defined radio to be able to sniff these Nordic chips without the use of dedicated hardware and to see 100% of the received packets. So we have some GNU radio blocks we're using out of the box. It's a low-pass filter and the demodulation and modulation. And then the new code here is a framer and deframer for this enhanced shock burst packet format. There are some quirks with SDR that you don't have with the HDR. So with the HDR, you can tune very quickly on the order of 250 microseconds. Most commercial SDRs just can't tune that quickly. So if you're working with a frequency hopping protocol, the SDR implementation isn't going to be very useful. And then you have the problem of responding to ACKs. So say you're receiving on your host computer, you want to receive a packet and reply to it with an ACK. In the time that it takes for you to receive those IQ samples and know that you need to send an ACK, the shorter ACK timeout windows will have already elapsed. So depending on the vendor-specific implementation, they have ACK timeouts as low as 250 microseconds and up to 4 milliseconds. So this will be compatible with some of the parameter configurations, but not all of them. And so there are 3 main classes here. We have Nordic_RX, and this consumes bits that are spit out of the GFSK demodulator. This attempts to reconstruct the enhanced shock burst frames, then it prints the PDUs to standard out, and it also sends them to a Wireshark dissector, which I've written. Then we have Nordic_TX. This is the inverse of this. This consumes this Nordic tap struct, produces enhanced shock burst packets as a byte stream, and sends those out to be sent over the air. Then we have this class enhanced shock burst packet. This just encapsulates these enhanced shock burst packets, and it generates packets as well as has a logic for reconstructing them from the incoming bit stream. So the Wireshark dissector is pretty straightforward. It has the simple Nordic tap format. This has all of the fields that you'll have in the enhanced shock burst format, as well as the address, payload, and CRC. If you haven't written a Wireshark dissector before, I hadn't. Doing it in Lua turns out to be very, very simple. It's maybe 30 lines of code for the dissector, surprisingly accessible. And again, so the dissector is written in Lua, consumes these Nordic tap structures, and then spits out data in Wireshark. So now I'll do a code walkthrough and then do some live demos here. OK, so here we have the enhanced shock burst packet class. And so the constructor, it takes in these parameters of all of the properties of your packet, and then it builds the byte stream that gets sent out to your GFSK modulator, for example. And so we're building the header here. We're appending the payload and CRC, calculating the CRC. Then we have this try-parse method. This consumes an incoming byte stream and bit-shifted byte stream. So we have bytes here. This is the incoming byte stream. We have byte shifted. This is the incoming byte stream shifted by 1 bit. The reason we do this is that the packet control field is 9 bits long. So we have some of the fields we need to look at one offset, and the rest of the fields we need to look at some other offset. This is actually produced by a class here called bit shifting byte vector. So this allows you to append one bit at a time to this circular buffer, basically, and then you can access any offset of the buffer. So we put bits into this buffer, and then we can quickly access the most recent offset as well as 1-bit offset for parsing these packets. So try parse attempts to look for valid packets. If it sees one, then it spits it out, and then the Nordic RX class here then calls try parse. When it has a successful packet that was decoded, then it builds the Nordic tap header to send to Wireshark, sends it to Wireshark, and then uses a message port to post this to whatever is going to consume that. So in this case, that might be putting it to standard out or what have you. And we have Nordic_TX. This is the inverse of this. This uses a message handler to receive a Nordic tap struct. It then constructs the packet and then returns the output bits, which are then sent to the GFSK modulator and transmitted. So we have a few Python classes here which then use the C++ classes. The simplest one here is called Nordic Receiver. So this is a single channel receiver. So this uses a Osmocom Osmo SDR source. You can use it with any SDR. This consumes the incoming IQ, decodes packets, and then prints those packets as standard out and sends them to Wireshark. Then we have something called Nordic Auto ACK. This is the same thing, except it functions in receive mode. It will listen for packets coming from another Nordic device. When it receives a packet from one of these Nordic devices, it will generate an ACK and send that ACK back to the device. So this demonstrates that we can do two-way communication between the SDR implementation and the hardware implementation. Then we have something called Nordic Sniffer Scanner. This scans between channels 2402 and 2484. When it receives any packets from the device, it camps on that channel for some duration, approximately 1 second. And the idea between this is we can sweep through all of the ISM channels, look for packets, and then send those into Wireshark. Then we have Microsoft Mouse Sniffer. And this is a little bit more specialized implementation. So the other scripts were set up to look for generic Nordic packets. This takes advantage of some knowledge of how the Microsoft devices operate to follow a specific Microsoft device. So in the case here, we have this Microsoft wireless mouse. This mouse can operate on one of 24 channels, but that's split up into 6 groups of 4 channels each. And the way this works, each device will operate on one group of channels. So this scans through, looks for a device that appears to be a Microsoft device. When it finds one, it then cycles through those 4 channels in that one group and uses that to follow the device quickly. So I'll go ahead and do a demo here with Nordic Receiver. This will be a single channel receive demo. And so to transmit, I have a Logitech unifying USB dongle here, and I flash this with my custom firmware that makes it possible to do arbitrary packet transmission from this dongle. And so what this is going to do is attempt to ping a device on channel 4. And so it doesn't have any success in pinging the device. There's nothing listening, so it's constantly trying to ping on this channel. So now I'll go over here, and we will run the Nordic Receiver script on channel 4. This is going to be listening using this usurp, and will be decoding the packets that are transmitted by that Logitech dongle. Then while that's flashing the firmware image, I will go ahead and open up Wireshark over here. And with the Lua script with Wireshark, you can install it, or you can simply execute Wireshark from command line and pass in your Lua script if you're doing quick iteration that way. OK, so now we have this. This is printing to command line here. Just 1 second. So this is actually saying ACK packet, but that's it's incorrect there. So this is just doing receiving here. So I'll go ahead and open up Wireshark. And now we're seeing all these packets that are being transmitted by this Logitech dongle. So here we can see the channel, rate, all the properties of the hand shockwrist packet, including the address and payload and CRC there. And so this is demonstrating that we can then receive packets being transmitted by one of these hardware Nordic chips. So now we'll go over here and stop this. And so this is constantly trying to ping on channel 4. So the next thing we can do is run this automatic ACK script. And this will receive one of these pings and reply to it with an ACK. And the Nordic chip right now is running a very wide ACK timeout. So it's a 4 millisecond ACK timeout, which is possible for the SDR to respond to. So I'll run this on channel 4 here. This then replies to the ACK, and we can see we have ping success here, meaning that the ACK was successfully received by the Nordic chip. So now we can go over here and run the Nordic sniffer scanner script. This will sweep between 2402 and 2484. So I'll run this, and I'll open up Wireshark, and we'll see what other Nordic devices happen to be running in the room now. So here we have, let's scroll down to the end here. Restart Wireshark. So now we have some Nordic devices which are not devices that I am currently transmitting on. So we have this. This should be classified as a Logitech device. It's not currently, but we can see from the address. With these Logitech devices, you'll have the last octet ending in 07, and this is a Logitech, looks like a mouse packet here. So we have this device, and this is cycling through all available channels. Now this is camping on channel 2405, likely somebody is or was using their Logitech mouse. We'll just kind of scroll down here and see what else we see. So this actually looks, this packet is not changing. So this might be a Logitech mouse which is turned on, trying to ping its dongle in somebody's laptop bag, perhaps. Here we have Microsoft mouse. This is actually the mouse I have. This is turned off. This is somebody else's Microsoft mouse, it turns out. So somebody has a Microsoft wireless mouse. They're using it. We have some ACKs there. We have some more Logitech payloads here. So the point is that we can quickly scan through and see a lot of different interesting traffic using the SDR. So now we'll go and look at the Microsoft mouse following demo here. And so this will start by cycling through the 24 channels that the Microsoft mouse can use. So I'm going to plug this dongle into the computer here and turn on this mouse. Oh, this is looking at somebody else's Microsoft mouse. And because that mouse stopped moving or stopped receiving packets, it then kept cycling again. So it will lock on at some point, but then when it no longer sees that device, it will then continue scanning here. So here we have somebody currently using their mouse. If you're moving it, you know that's you. I'm going to restart the script because once it locks onto a Microsoft mouse, it then continues to follow that mouse indefinitely. So we'll see if we can get it to lock onto my mouse here. Okay, so I'm moving my mouse around here, and we'll see if it finds it. Okay, so this is the address of my mouse here. So we're seeing a lot of ACKs coming back, and then some mouse movement packets. We can go back over to Wireshark. We can see all these, ACKs and then other packets coming in from this mouse. And so the point is here we can have now packet reception and transmission with arbitrary Nordic nRF24L devices. And the Wireshark dissector is surprisingly simple, so extending this to classify other types of devices will be pretty trivial. So the Lua code is very straightforward. You're simply parsing a struct, doing a little bit of logic, and adding some fields to a tree. I had no idea Wireshark dissectors were this simple, but it turns out to be pretty easy to do. And that's what I've got. Any questions?
Okay. Do we have any questions for Mike here? There you go, Raj. I got him.
You kind of casually mentioned that you'd reflashed a Logitech Universal dongle to be able to send and receive arbitrary stuff. Is that part of your stuff, or is that a publicly available firmware?
Yeah, so let me go back here. We have the firmware that I released for these dongles available on GitHub there. And that allows you to flash this onto either the crazy radio dongles or anything over SPI, or with these Logitech dongles, using that firmware update process, you can just run sudo make Logitech install and flash that firmware onto these Logitech dongles.
Other questions for Mark?
Sorry? Oh, it'll be, so the code for the SDR implementation will be up on GitHub in about 10 minutes.
Did you also, I guess, reverse the payload? Could you actually trace out the mouse?
Yeah, so on in that same GitHub repo, there's a white paper from a DEF CON talk I gave, which has payload formats for 16 different vendors' mice and keyboards.
Regarding the ACT timeouts, you set to like 4 milliseconds?
Exactly, and that's the maximum. It can do, at least with this laptop and SDR, around 2 milliseconds.
Okay,
is
that
the
was going to be
lower
my
bound.
question. What was the minimum that you found?
And in practice, a lot of these devices will have fairly wide ACT timeouts. So 2 milliseconds is realistic, but I haven't characterized across the board what the common ACT timeouts are.
Any others? Raj, Jose, can you get down to Raj? Sorry, if we don't have a mic, they're not recorded, and they won't be part of the recording that gets posted.
Is any of this part of the challenge, Balint? Well, either of you. I mean, can you? Wouldn't it be great if this was somehow part of the challenge?
It'll be on GitHub soon.
All right, so I guess to follow on to that, do you have a PyBombs recipe once it gets onto GitHub?
Nope. I've actually never used PyBombs.
All right.
Let's do that on Friday.
Sounds good.
I'll have that done shortly. All right. Thank you, Chris. All right, any other questions for Mark? No? All right, let's thank our speaker.
Thank you.